In this video, I want to take a look at reproducing the monitor source code for the Lawrence Livermore Laboratory MST-80B computer. So Lawrence Livermore Laboratory produced the MST-80 and the 80B in the 70s, and these were basically single board computers that came in a briefcase. They were meant for teaching microprocessors to people in the world. I'm 99% sure this is the briefcase computer I used in my short time in college. I could be wrong, but this seems really familiar. There's two versions of the system. There's the MST-80 itself. That was the original version. You can tell it's an MST-80 because to the left of the hex displays is a jumper block, and that jumper block could be used to configure those displays for either hexadecimal or octal output. In the B, the monitor's been updated to produce hex or octal, and there's actually a button on the keypad that will select hex or octal. So I've got a unit that currently doesn't work. I've been able to pull the 1702A EPROMs out and dump them, and it doesn't have the monitor. It's got some application in it, so I need to recreate the monitor. There's a bunch of different versions of the manual. I'm looking at the 10.379. I believe it is version, or boy, that's hard to read. June 15th, 79, and the source code has a header in it that'll tell us that. So there's a bunch of information here. That's kind of what the system looks like. The system, well, we don't need to go into the system. We'll look at that separately. We're really looking here at producing the source code. Like I say, if it's an MST-80 original, there's a jumper block right here next to the displays. This HO key here toggles the display between hex and octal on this MST-80B, which is what I have. And it gets into the system and the syntax and I/O. But in the back of the manual, when we get there, as I scroll down, we'll get there eventually, good Lord, is the source listing. So this is the source listing for the monitor. It's actually a list file dump from their macro assembler. And basically they've assembled it, then they put the, like I say, the list file output into the manual. The list file output basically has all of the addresses and the opcodes that were generated, etc. in it, in this format. So my process was to take each one of the pages here of the list file, OCR each page individually. I found a decent online OCR site, collect all those text files back, put them together, and then begin to clean it up to turn it into an ASM source file. I am using the Telemark assembler. Don't let TASM here confuse you with Turbo Assembler. This is the Telemark assembler. As far as I can tell, it's now freeware. It works with Windows really well. It works under Windows 10. There's a 64-bit version of it. It's a nice little assembler for me in that it supports 6502, 6800, 8048, 8051, but 8080, 85 are here, the Z80, and some other stuff. So just so it's said here, the 8080 and 8085 mnemonics for the assembly language are not the same as the Z80 mnemonics. And this listing is in 8080 mnemonics. It's not in Z80 mnemonics. So a Z80 assembler wouldn't understand the mnemonics and would fail. I've converted 8080 source to Z80 source enough times to know it's a pain. But in this case, it can deal with 8080, 8085 opcodes directly. There's what's called a tab file. You provide a tab file to the assembler that tells it what the target's going to be. We'll look at that here in a bit. But there's good online documentation here. Just search for the Telemark assembler. You'll find it. I use this for pretty much all my projects because it runs on Windows. The assembler switches, etc. are the same no matter what the target is. It works well. With the 6502 tab file here, I've been able to reproduce the Apple I monitor and the Apple I Basic. Byte-level-compatible, exactly the same as what WAS did, and that's from disassembling the source code to clean up to assembling back to an object. So it works well. Like I said, I've bit level reproduce those. I've done Z80 stuff on it quite a bit. In this case, I'm doing 8080 stuff on it. And for me, it just creates a single environment that works well. The documentation here is solid. It takes a little bit of time to understand the switches and how they work. But like I say, the documentation is really solid, and it's worked well for me over the years. So we're again back looking at the manual here with the list file in the manual, and what I converted over to, like I say, source. And My source doesn't match this exactly, and there's some reasons for that we'll look at. So we can see here at the top about, there's hex-octal monitor for MST-80 microprocessor trainer. I've captured that here as well, written by Gordon Jones. This shows the 31479 version. I'm actually working in the 82376 version, and there's a different document. There's a different, documentation package for the system that has this source in it. I don't know why I have this one opened. It honestly doesn't matter for the conversation here. So some notes here. When you're thinking about the 8080, the 8080 is really thinking back in pages and the page. Well, very much like the 6502 does. The lower 8 bits of an address are the contents of that page, and the upper 8 bits point at a page. So there's 256 pages and 256 bytes. So the hardware on the MST-80 has RAM starting at location 0700 hex. So page 7 is RAM for register, storage, and stack. There's some equates here. This is a place where syntactically it's different. Their assembler used EQU. Basically, take this label and equate it with this value. And the telemark assembler, it's an equal sign, so there's a difference. But besides that, it's identical. 07B7 hex, 07B7 hex. It can do simple math like this. Take the value of this one and add 2 to it, so that O flag is 2 bytes beyond that location. Page 5 has the memory map keyboard. So the way the keyboard works is it's literally mapped into memory. So you may be used on the 8080 and the Z80, you're using ports for I/O. You can also do memory mapped I/O on those platforms, the same as you do on the 6502. It's just put something out there, get something back, whether it's memory or ports or whatever. Some other equates here for not exactly sure what all these are used for, but there's another set of equates here. Something that was interesting to me is in the original OCR, most of the B's got interpreted as 8s. So this was 787 hex, 789 hex, 78A hex, 788 hex. And that really threw me for a while because I was looking at the list file output and comparing the bytes to the bytes here in the listing and not getting matches, and finally realized like I said, the OCR had misrecognized these and put 8s in for Bs. But that led me to realize that this break store address is the same as this PC store address. And that seems really kind of odd to me, but that's consistent through all these listings. I would almost think that's a bug, but I've left it that way intentionally. I've added a couple comments here. Port 0, when you write to it, is for the hex or octal displays. You send a byte to it and it'll get displayed as octal or hex. Port 1, right, is a user port. So there's a user port that's latched, and there's a user port to read, and that's on port 1. We get into the actual code here. In the actual code here, there's an ORG statement. So org0 says basically start. What does it? It says start at address is 0. In the telemark assembler, that syntax is current location equals address. So that's the equivalent of org0. The numeric values formatted the same, so that's 070 or 07F0 encoded in hex. The H says hex. That's pretty common syntax. Here is our interrupt vector table. So we're going to set the current working address to 20 hex, and the vector it finds there is jumped to this address. And then there's another interrupt and another interrupt. I think there can be up to 8 of these. No, that doesn't seem right. There's some number of these that can exist. There's 3 that were added at some point. If we scroll up here to the comments, we'll see that in 31479, Gordon Jones added vectors for interrupts. This code over here doesn't have the interrupt vectors, as I recall. No, it does, actually. So, again, I have a lot of confusion about version and dates and source and what they really contain. And finally, we've got our entry point at addresses 0000. On reset, the 8080, the 8085, and the Z80 all jump to addresses 0000 and start execution of whatever byte it finds there. So we've got our system initialization here. Load immediate the stack pointer to that address, clear the AC register, initialize storage display, etc., etc. And there it is. The system initializes. There's a command table down here that I believe has the byte offsets for where the commands are all going to live. It seems to be. And then we start the actual system code. And there's a break routine that takes care of, you've hit a break. There's a keyboard read routine. Like I say, it's memory mapped. Bunch of routines here. I'm looking for particular things to point out here. So here's a good example. 0BB hex. So the reason this is a byte, so it's defining a byte, but it needs deleting 0 because if it started with an alpha, the B, it would assume it's a label. So in this case, the syntax was I had to have a 0 to say it's a numeric value, the value, and then the H is saying interpret that as hex. Without that leading 0, you get an error here. It would think it was looking for label BBH. I tend to put the zeros in just for consistency to make it look like a full byte. Here's an example here where we don't need the leading 0, but it's there just to make it look clean. And I believe the programmer over here followed the same kind of source code logic here. However, is an inconsistent one. So let's go ahead and add a 0 just to make that more consistent. And that right there told you I'm not using tabs. I'm actually using spaces inside of the file here. Scream at me if you need to. I'll ignore it. In this case, to me, it just doesn't matter. So we've made that a little bit cleaner. There's another 0f0 hex. Again, leading 0 so it knows it's numeric. Here happens to be a octal value, so Q. So following the numeric string with the Q, it says interpreted as octal. So that's 370 octal. It is what it is. They used octal in the listing over here as well. Another 370 octal, out port 0, and immediate with 3 octal. That should be able to be written like that. It shouldn't honestly matter. Maybe we'll blow it up here. It shouldn't. I mean, that's a full 8-bit value in octal. So 2 bits, 3 bits, and 3 bits for a total of 8 bits to get a byte. 160 octal. Let's go ahead and just for consistency here, I really prefer cleaning stuff up like that. And finally, we get down to the end of the code. There's a numeric key code table here that it uses to do lookups of what key on the keyboard was hit. So challenges I had in the conversion of this was things like the Z here was either interpreted as an ampersand or I think at times an S via the OCR, and I had to manually clean those up. On lines like call 1, there was a syntax error here. I think that had L ampersand I. I think the X got interpreted as an ampersand. And so this was a syntax error. And because of that, the label column 1 was unknown. And so any place there was a call to column 1 or a jump to column 1, you got an error with undefined label. And so there was a lot of noise for undefined labels that I had to work my way down to where the label was and actually get that to compile correctly. Almost all I had to do was, like I say, X ampersand, Y. In ampersand, I think, was fairly common. It had trouble sometimes with C here, jump if not carry, and Z, etc. That kind of confused things. The PCHL, the CH kept getting seen as 0B or something. It was consistent enough I could actually do a mass replace and get things better. But this, we'll go ahead and save it because we've made some tweaks to it. At the machine, the machine I'm working on itself, this of course is a command shell on my Win 10 machine. We have our working folder. We're working with the 1702A EPROM, but under the ROMs, we're in the source code folder where this source lives. And let me go ahead and just pull up all the files here. There's a batch file that actually builds the code, and we'll look at that in a bit of detail. There is the assembly file that we were just editing. There's some output files here, a hex list and symbol we'll look at later. This is something I'm doing myself that doesn't matter in this conversation. There's the telemark assembler here, and there's that tab file we talked about. TASM85.tab deals with the 8085, and then it deals with the 8080 opcode syntax. I tend to put the tab file and the assembler in the folder I'm working in. They're pretty small. I don't care how many of these I get, across the disk. These are static, they don't change. It just makes this, I can zip this folder up and it's a complete project in one folder. Like I said, I wrap it in a build.bat file, so build.bat. If we look at build.bat, we can kind of talk through what it does. Anybody familiar with Windows batch files will recognize the syntax here. Echo off just says don't echo these out before you execute them. The line CLS clears the screen. If there's a list, hex, or symbol file, it will delete it. Or no, it notepads it. That's a typo. Wow, how long has this been in place? And I missed the fact that those were supposed to be deletes. I added these a couple days ago, these three in here, to kind of do the equivalent of a clean. If you used make files, you could do a clean here. And I could use some kind of make file system to drive this. I just haven't done it. So if there's a list, hex, or symbol file, go ahead and remove them. Let's go ahead and stretch this out wider because it'll make this easier to see if I can get on it here. So here's the TASM command line. I put comments up here to kind of indicate what the switches are. So -T85 says use the 8085 tab file. I want labels output into my list file. I want symbols output. So I want a label table and a symbol table output. -G is the output format. 0 happens to be Intel hex. In that documentation, you'll find what 1, 2, 3, etc. are. In the hex output file, I want 8 bytes per line. It defaults to 24 bytes per line. I want 8 bytes per line, and look at why in this case. This, by the way, is a hex value, not a decimal value. So a 10 here would be 16 bytes per line. So just, if you ever muck with this, keep in mind that's a hex value. We're going to output hex data into the list file again. I want a hex dump as well. So the list file will contain a label table, a symbol table, and a hex dump. And we'll look at what that format is. And then the output files, assembly file, hex file, list file, and symbol file. And at the command line, you'll see me do build space monitor. And this %1 becomes that argument, the monitor. It gives me a directory of what's in the folder. If it finds a list file, it tells Notepad++ to open it up. That actually gives Notepad++ focus, and we'll see that happen. So we're in the batch file here. Let me run that batch file. So build, and I'm in this case monitor, and I'm sending it monitor because that is this part of the file name. For my code, it's compiled it, yes, or assembled it. It's very quick. It's opened up the list file here, and it knew the list file had changed, so it opened up where it was before. But here's our list file. So, we can see the comments we had at the top you looked at. We can see where the equates live. We can see, what all can we see here? Some more comments I put in. We can see where they originally had an origin 0, and I've got the current working address is 0. And we can see that happen here. There's the current address the machine is working at. So there's address 000 in the output, which is this byte. And then 0001 is here, 002 is here, and then 003 in the address space has an AF. So this is an indication of the address here that the opcodes live at. We have the initialization opcodes, we have that lookup table, or offset table, whatever that is. We can see here where the origin has gotten changed to 20 hex. We can see that we're now at address 20, and here happens to be a jump to 0280. And that matches what we have over here, jump to address 0280 hex. Again, set the origin to 28 and to 30. That is the vector or interrupt vector table. So this is one of the things that was added later on, was if different types of interrupts occurs, there's a jump address, there's a vector for them. Our source code, so we've got our initialization source. This sits at address 0000 because that is the address that the 8080, 8085, and Z80 on reset begins execution at. Where the 6502, if you're used to it, will go up near the top of memory and get the reset address vector and jump to that address. This Intel architecture just goes to address 000 and begins execution. And that's why typically on an 8080 or Z80 machine, you'll see all the ROMs in low memory and the RAM above it. Whereas often on a 6502, you see RAM in low memory and ROM someplace above it, and that's because of the way it deals with resets. So really, we have our code that starts here at address 38. I've already spoke a little bit to the fact that there was a lot of issues with OCR that took me a while to clean up. It's giving us, like I say, at address E6, there's a C3, E7, E8. At EB, there's a C3. at EC59ED00. Again, this is working in hex. So work our way down the list. There's the end. There's no error count here, so there was no errors. This is that label table that I asked for that basically says this label is at address 0134, this label is at 0152. It's got all the labels and where they are at. And they are in sort order across. So A, B, S, B, O, B, well, that's not quite true either. Are they in sort order? They're in an odd order. I'm not sure what that order actually is. Anyhow, there is that hex dump I asked for. So at address 000, there's a 31. And at address 180 hex, there's a 09. And sometimes being able to copy this out and edit it for something else can be useful. This can be useful to me and has been many times. There's the number of errors down here. Number of errors is 0. So we got our symbol table. We got our hex dump. I didn't get a label table in here. Does it only do a label file? That might be. If we go to the monitor.hex file, it'll say, hey, it's been updated, which it has, although nothing changed. If you're familiar with Intel hex files, you've got the address right here, that the opcodes, that the bytes get programmed that into the target device. You've got the actual bytes to be programmed here. So you've got a prefix of 00, and you've got a postfix in this case that is an 8-bit checksum, and that's the checksum for the line. And then starting at hex address 8, as this set of bytes get programmed, at hex address 10, this set of bytes gets programmed, and we can see that runs up through 18, 19, 1A, 1B, 1C, and this is where we then did that change the origin to 20 hex, 28 hex, and 30 hex. And that's why these look different here. There wasn't a full 8 bytes to fill this one out, and there was only 3 bytes at these locations. Again, it wasn't filled out. And then if you remember, we set the current address to 0038 in the source. And here's our dump of the ROM, or the data to go into the ROM. One of the reasons I dumped this 8 bytes wide is when we get, in this case, is when we get down here to 00F0, these bytes get programmed into the output device, and that's actually, this is the last set of bytes. I'm off the line. This is the last set of bytes to be programmed. Let's get them all selected into the target ROM. So for 1702A, you've got 256 bytes. And this is F8, F9, FA, B, C, D, E. This byte here happens to be FF hex, and that's 256 decimal. So this byte right here is the last byte in the first ROM. So the first ROM, the first 702, lives in page 0 because it's 256 bytes in the EPROM. And then we move to page 1, and the second EPROM picks up. And smart enough EPROM programming software will let you say, I want to offset the data programmed into my ROM by, in this case, 100 hex. And so when you drop ROM 2 in place, it would start its first address with C3 and would program on up. I'll figure out how to deal with this as we get to a 1702 programmer. We'll look at it when we need to. But from here on down is what is in the second 1702. So the page 0 EPROM, the page 1 EPROM. So there's a little bit more here. These 2 bytes end up in it as well. Like I said earlier, the 67 in this case was a checksum. And then there's an indication here. The 00, the 00 and the FF tell it that you're at the end of the file. Syntactically, I don't know if you've noticed what this is formatted or not as. There is a count, that's how many bytes are to be programmed. There are the bytes to be programmed. They are going to this address. There is our prefix that says the bytes are about to come. Byte to program, byte to program, byte to program. And the checksum for the end of the string. So it knows that once it gets to 8 bytes to program is done, there's a checksum byte. And whatever's reading this file in needs to understand how to interpret this. This is an Intel hex file. There's other formats. We asked it to generate a symbol table, which it's done here. And in this case, about to say they are in sort order, but they are not. I guess they're in sort order for the first letter only. I didn't realize that until looking at this. But this basically tells me that the label in the code for the break BRK is at address 38. And if we go back to the list file and we look for address 38, which is right here, we see BRK. If we take a different label, load keyboard at 071, we should find HIJKL, load keyboard at 0071. So it's just a way to find the byte offset easier if you're looking at it. We've looked at the hex file, we've looked at the symbol file output, we've looked at the assembler output. Let's go ahead and introduce an error here. I'm going to change move to M0V. So I'm going to actually inject an error here intentionally, and we'll look at how things happen when we assemble this. So let's go ahead and save that. Let's build it again. It tells us that the list file has been updated. It's telling us that it can't find label LUT. So right here is a jump non-zero to label LUT. It can't find label LUT. It doesn't exist. And if we get down to where that error actually occurred, right here is label not found, LUT, value misaligned, unrecognized instruction. There's what we wanted to see. There's an unrecognized instruction. Oh, I have M0V. Might take you a little while to work through interpreting these. It's a little bit like an early C compiler, where an error way down deep in the code can cause all kinds of errors above it that just aren't real. In this case, there is no LUT label created because this line didn't assemble correctly. So if we go back to the source and we change that back to an MOV, move. This is one of the reasons I use Notepad++, is I get syntax highlighting. It knows it's in a SEM file, and there's a bunch of words that it knows what they are, and it makes them blue. I could probably add these strings to that so they were all blue. I just haven't taken the time to do it. Save that out. Build it again. The error went away. If we get down to the bottom, it'll tell us there's no errors at this point. Previously, there would have been 2 or 3 or 4 or something errors there. I don't know how many. So when I first started to build this, it started with a large number of errors. I don't know how many, and I slowly had to work through it until, like I said, I got a clean compile. I had issues where the OCR was interpreting BB as 88. I think I've mentioned that. There was OCR errors that were pretty consistent. It took a while to figure those out, but once I got it assembling cleanly from the list file, I then went to back to the manual, and we'll blow this up here, and I did a visual comparison. So let's get up to the first page here. So it should start with 31F007, 31F007, followed by an AF32B707, AF32B707. I worked through this several times until I got the exact same byte sequence. So when these were 88 in the source and not BB, you would have anything pointing at these, pointing at an address that didn't match. There would be an 88. Someplace in the data stream rather than a BB, and it took a while to understand what was causing that. But like I said, this is how I confirmed it was creating byte compatible output. Oops, I want to grab this one. If I can get it to grab here and drag them both. Such a pain. Anything else to really chat about here? This was the process. Of course, at some point I will make all of this available for anybody else wanting to muck around with their MST-80. Just to mention, one of the people who follows me on Twitter dumped his ROMs and provided them to me from his unit, and it was identical till the delay routine here. And once I disassembled what was in his delay routine, it's actually maybe a little better structured delay routine, and then it's not relying on the opcode time for these two here to generate extra delay. There was actually an inner and outer loop. I just think it was a little cleaner delay. I haven't actually put that code in here. I may at some point. This does leave us a little bit of address space left, so from address 182 to 1FF, we have the ability to put our own stuff in if we want to. And then the MST-80 has a third 1702 EPROM socket at page 2. So there are another 206 bytes there that you could put code into as well. So, 768 bytes of ROM total. That's 3 1702s at page 0, 1, and 2. Anything else I wanted to chat at in this video? Anyhow, there's the review of the code and what I did to build this all up and get the source code captured and assemblable. These are the steps I went through. I think I already mentioned I'll make these freely available. If you found this useful, I'd appreciate a like. If you haven't subscribed and think it's useful content, give me a subscription. Always appreciate comments. I guess with that said, if you got this far, I appreciate it. Thank you, and I'll see you in a future video.